Hello everyone. Today, I'm going to be talking about what is known to be the observer design pattern typically used in event-driven systems. When talking about the observer design pattern, it's important to talk first about its two critical parts, the first being the observable subject. This is an object that can change state, usually unpredictably, but which can be observed. A subject is essentially something worthwhile to look at, something that you pay attention to because it informs you of something important. A scoreboard, for example, is an observable subject because it tells you the score of each team or player of whatever game you're watching or playing in. The scoreboard is the subject, and you, the person looking at the scoreboard, are what we will call an observer, the other critical component of this design pattern. An observer is anyone, be it a system, device, or server, that observes the subject and may or may not react based on whether there are changes to the subject. Thus, a subject has observers. But it's important to note that it doesn't necessarily need to have one to be a subject, only that it is observable. A scoreboard can exist without anyone looking at it. If there's a tree in a forest and no observer is around to see that is tree standing has been set to false, it doesn't change the fact that the tree can still be observed, it just currently isn't. Going back to the scoreboard example, you might want to know which team or player is winning, so you look at the scoreboard. If the scores on the scoreboard change, it might change the knowledge of who is winning. Now this begs the question. If you want to know who is winning coupled with the fact that the score, and thus the one winning, can change unpredictably, how do you get that information? In other words, how do you get an observer to know if the subject has changed state? In our example, we just have to look at the scoreboard and we would know. And this is actually an example of one of two ways to distribute this kind of information. Polling. Polling is when the system that needs to know something just checks on the external system that actually knows what that something is. In our example, you are, in a sense, polling the scoreboard by looking at it. You look at the score. If the score hasn't changed, then you don't need to mentally take note that someone else is winning. It hasn't changed. If the score has changed, then you need to evaluate if someone new is winning. You have to put in some effort if something changes. Another good example is pictured here. In many social media apps with a timeline such as Twitter, Instagram, and YouTube, you can do what's called pull to refresh. That's a poll. Your client app asked the servers, or polled them, to see if there are any new tweets, reels, or videos that the server replies with the relevant answer. And your client, depending on the answer, may choose to get these new posts with all the relevant data, such as who posted it, how many likes does it have, or just the post itself. There is, however, a caveat to this. Remember that the observable subject changes unpredictably. Thus, for each observer to be relatively up to date with any state changes made to the subject, it's required for each observer to be regularly checking the subject. You don't necessarily know when an update will occur. In our scoreboard example, if it's important for you to know who's winning at any time, say you made a bet with your dad, you would have to constantly be looking at the scoreboard so you will know, pretty much always, who is in the lead. Now, suppose you have 23 other people that have a similar bet with their dads. Now you have 24 people looking at the scoreboard very often. Some may not even have their attention off the scoreboard, so they're just constantly looking at it in case the score changes and thus the leader changes. But let's be generous and say that these 24 people are looking at the scoreboard once a second. Essentially, this is a system wherein a subject has 24 observers, and each observer is sending one request every second. If this system happens to be running 24/7 and the observers also run 24/7, the system would have to deal with 2,073,600 requests a day, when extending to a year would have to deal with 756 million requests per annum. And this is just the traffic for one subject with only 24 observers. Imagine if the number of observers or the rate of polling increased. What if hundreds or thousands more people have a bet with their dads? What if every tenth of a second in the game counted? At some point, it will become infeasible for the system to adequately keep up with all the requests coming in from the observers. Limitations of bandwidth or processing power will arise very quickly. The system could theoretically be able to reply to all of the requests, but with limited bandwidth, responses could lag because there's a bottleneck. The limited bandwidth allows only so much data to flow in and out. On the other hand, the system could theoretically handle the inflow and outflow of data, but be unable to deal with all of the requests at once because of a limitation of processing power, again, causing responses to lag. So how do we deal with these potential issues? Well, one solution is to not poll at all, and instead utilize the second way of distributing information changes, pushing. Now, as we said earlier, polling is the act of checking the status or state of another external device. Pushing is when that external device, the one that would have been polled, instead notifies other systems when changes occur. That's where the push in push notification comes into play. A push notification tells you if a new tweet has gone up, or a new video has been uploaded, or a new message has just been received. Instead of you refreshing Twitter, refreshing YouTube, or refreshing Messenger for new stuff, those apps just tell you when there's something new to look at, saving you time and energy. In our scoreboard example, instead of you having to constantly check the score, where a lot of times it might not even have changed at all, the scoreboard is the one taking the initiative and telling you that a change has occurred. When pushing information, the subject is responsible for broadcasting its updates to all the observers. Depending on how often the subject changes, this can dramatically decrease the load that otherwise would have been required if each observer had to constantly poll the subject for updates. Think about it. If those 24 people who now have to pay their dads a bunch of money were instead just informed of any changes to the score, instead of constantly checking to little avail, they would have had their time saved, their energy not necessarily wasted, and the amount of work the scoreboard's interface had to perform would be a fraction of what it ended up actually being. This is the observer design pattern. It's a software design pattern wherein the subject maintains a list of its observers and notifies them automatically of any state changes, usually by calling one of their methods. Now that we've established what this pattern is and why this pattern is, we can talk about how to implement it by an interface or an abstract class. Starting with the observable subject. By definition of the design pattern, the subject must notify all of the observers of any changes. Thus, it would make sense that the subject knows every one of its observers. The subject must have some sort of list or collection of all of its observers so that when an update happens, it knows who to notify. Of course, this means there's a way to add and remove observers from this collection, and that's why there's a register method to add an observer and a deregister method to remove an observer to the subject's collection of observers. And finally, when an update does occur, the subject must have a way to actually do the notifying. It has the references to each observer in the collection, so the function notify observers simply utilizes that collection, effectively letting them know that an update has happened and the observer might have to do something. What is that something though? Well, that goes into the implementation of the observer. The observer is simple in that all it really needs to do is observe the subject and act upon any changes to the subject. This is done by implementing an update method, which is what gets called by the subject when the subject calls its own notify observers method. What the update method does is dependent on the observer. It could be anything from requesting more information for display, writing the status to a file, running a calculation, it doesn't matter. What matters is that the observer has an update method callable by the subject when an update occurs. We can see all of these in the UML class diagram here. On the lower left side, we can see multiple concrete observers. They could be doing their own thing, but they both implement the fact that an observer has an update method, and that observer can exist independently of the subject, with this diamond arrowhead connecting the observer to the subject. Speaking of the subject, we can see that the subject has a collection of observers, and that there are methods to add and remove observers from this collection. And finally, we can see that the subject also has the method notify observers and some pseudocode that tells us what notify observers does. It calls each observer's respective update function in the collection. And that's it. That's the observer design pattern. Hopefully, you understand how it works and why this pattern would be implemented in your system, and I hope you have a nice day.